Hello, welcome to the class on response surface methodology. Today we will discuss second order model, primarily how to fit second order model, the experimental designs required for data collection through experimentation, and then how do we estimate the parameters and check the model adequacy. Followed by the second lecture will be on analyzing the second order response surface model. So, content of this class will introduce the second order model, then I will show you the second order response surface design, which we have elaborately discussed in the last class, and then I will show you the how to fit the second order response surface. We will end this lecture with an example, which we will continue in next class also. So, if you recall the last but one, where I have discussed on the sequential experiments, that means, so we have the operating zone and you have started with experimenting somewhere here and the first order experimentation, and this will give you that you follow this direction and maybe your that optimum zone lies somewhere here. So, when using the first order model here, you get the direction of improvement, and then you start doing experiment one after another at different points, and accordingly if you plot the yield value, for example, the y and the your different experiments runs. So, last class we have shown you that the yield, what way the yield value is changing, and in this manner we come to some point like this. And then here we say that this is the such curvature. So, in at this point, perhaps this is the zone where the optimum point lies. So, this zone is a nonlinear zone, which is here it is probably quadratic one. So, at this particular operating zone like this one equivalent to this. So, here your first order model will not fit, you require second order model. And second order model, then if I consider the same example, that where we have two independent variable or factors x 1 and x 2, then the second order first order model we have explained. Okay. Now, let us do the general one. Suppose that we have k number of factors, k factors. So, x 1, x 2, x 3 like x k, then your second order model looks like this: beta 0 plus sum of I equal to 1 to k beta I x I plus sum of I equal to 1 to k beta I x I square. So, this is our main effect, this is the intercept, and this is the quadratic effect, plus there will be interaction term I less than j. So, beta I j x I x j plus error term will be there, plus error. So, this is your interaction term. So, by second order model we mean this, where there will be intercept, there will be that main effect or the first order effect, there will be second order effect, there will be interaction effect. Today class is for how to estimate this all beta, and then in order to estimate the all the beta parameters, what should be the experimental design, so that those many number of parameters can be estimated. So, because if we should require a experiment where the number of experimental runs should be sufficient enough to estimate all the parameters. At the same time, we should be cost effective, means we will not go for a large number of experiment which is practically impossible. So, here then what is the number of parameters to be estimated? One is beta 0, this is intercept. So, it is number 1. Now, your beta I, so I equal to 1 to k. So, that means there are k number of your first order coefficients, first order effect basically, or other way we can say main effect, first order main effect. Then beta II, that will be k in number. Okay. And then you see that you have the interactions. Interaction will be 2 interactions, 3-way interactions, and in this manner there will be kth way interaction. So, last one will be 1. So, you will be a large number of effect parameters. So, if I say that beta 0 is intercept, beta I, beta, these are all main effects, this is main effects. So, then there will be so many interaction, also there will be so many interaction effects. Okay. So, let us see that the difference in first order and second order model with reference to different factors. If you go for first order model, which is beta 0 plus beta I xi, then when k equal to 2, number of factor coefficients is 3, or number of parameters to be estimated is 3. And in that time, what will happen in the second order model? So, there will be one intercept, main first order effect, quadratic effect plus interaction effect. So, you require to estimate 6 number of parameters. If k equal to 3, in first order model number of parameters to be estimated is 4, whereas number of parameters to be estimated in case of second order model it is 10. Now, if your number of factors is 5, then you see in first order model you require 6 number of parameters to be estimated, but in the second order model 21 number of parameters to be estimated. Please remember, we are ignoring third and higher order interactions for the second order model. That means, only up to second order interaction, if we consider, this is the number of parameters to be estimated. So, as the number of parameters to be estimated grows significantly, what is required? You require a different kind of design, so that you will have sufficient number of information, and accordingly you will be able to estimate beta 0, beta I, beta II and beta Ij. So, if you recall my last lecture, there I said that in the response surface design, so we have given you the first order design, first order response surface design, and also we have given you the second order response surface design. So, in second order response surface design, we primarily say that central composite design and box Benken design. And again in central composite design, we say that is spherical and rotatable. So, depending on the value of alpha, so alpha will determine that whether it is spherical or rotatable, and in spherical case we say alpha equal to k to the power half, and whereas here in rotatable case nf to the power 1 by 4. And I also shown you that there is not much difference in case of spherical and rotatable, particularly for different case, and they are more or less equivalent in the sense a spherical one is also a minimum equal variance from the at a distance equal distance from the center of the surface. Okay. Anyhow, those things are known to you. Now, let us see that which one. Let us see the central composite design with two factors, and that part is that part looks like this. So, central composite design here, it has factorial points, your central point and axial points, and then depending on the value of alpha, alpha it will be CCD or rotatable, but here I have shown you a 2 to the power basically 2 factorial central composite design, where there are 4 factorial points 1, 2, 3, 4, 5, 5 center points and 4 axial point where alpha equal to root over 2. So, that plus minus root over 2. Okay. So, if you adopt this design, so how many experiments you are conducting? 1, 2, 3, 4, 4 plus 5, 9, 9 plus 4, 13 number of experiments you are conducting. So, if you go for a 2 factor case, so what is the second order model requirement? 1, 2, 2, 6 number of parameters to be estimated. So, here if we see that what are the distinct points are here 4 factorial point, 1 center point, another 4 axial points. So, from this figure you see 1, 2, 3, 4, 5, 6, 7, 8 plus central point 9. So, 9 unique points are there. We require 6 number of parameters to be estimated. So, number of observation is sufficient to estimate the parameters including errors. So, in case of 3 factor case, you may go for box Benken design, that also we have discussed in last class. Okay. So, for the time being what we will do, we will use the central composite design and we will bring the same example what we have discussed in last one lecture when we were dealing with first order response surface. Okay. So, let me repeat, a chemical engineer is interested in determining the operating condition that maximize the yield of a process. Two controllable variables influence process yield are reaction time and reaction temperature, and that is the natural variable reaction time and temperature. And then the engineer is currently operating with the process of reaction time 35 minutes and temperature 155 degree Fahrenheit, which result in yields of around 40%. Because it is unlikely that this region contains the optimums, if it is a first order model that applies the method of steepest ascent. In fact, the entire thing, all the steps procedures with reference to this example we have discussed in last one class, and I have also shown you that that the new zone of experiment will be this one, and the experiment what we have done with this operating zone, and we got this first order regression equation, and then we have followed the path of steepest ascent and we landed here, that this is the place or zone where the second set of experiment will be conducted. Okay. So, let us see that here at this point if we conduct a second order second experiment. So, what we will do here, what happened at this point, again we thought that there may be your first order relationship. So, as a result at this point with new your factorial points and new central point, the experiment was conducted. You see that at this place the factorial points are 80 and 90, 80 and 90 and 170 and 180, 170 and 180, and the center point is 85, 175, 85, 175. So, this is 180, 170, this one is 90, 170, this one is your again 80, 180 and 90, 180, and this is 85, 175, like this, with reference to this diagram, not with reference to x and y axis here. Okay. We have adopted factorial and central point here, and in the same manner we have fitted the first order model, and the first order model fit, when we have done, we found that the interaction and pure quadratic checks imply that the first order model is not an adequate approximation. So, I am not explaining here further that why first order model is not fit, the calculation we are not giving, because the similar calculation we have given you in the first order model. You just repeat the same procedure, and with this data what you will find out when you check the first order that is pure quadratic and the interaction effect, you found out that they are significant, and as a result what happened, first order model will not work. So, the curvature in the true surface may indicate that we are near the optimum, like here the curvature is there. Okay. So, that means you require a second order response surface. Now, to get the second order response surface, means by saying to get the second order response surface means to fit the second order response surface, what you require? You require more number of observations, otherwise you will not be able to fit estimate all the parameters. For example, if you do these 4 factorial points and 1 central point, then what happen? There are 6 distinct observations. 6 distinct observation in the sense, at the central point whatever 5 observation there, at the same point we are treating them as a single distinct observation. But you require 6 number of parameters to be estimated. So, here number of parameters, all parameters cannot be estimated, also error cannot be estimated. So, what we have adopted here, that we have adopted the central composite design with factorial points, central point and axial points. Please note that this ultimately this example I have taken from the Montgomery Design Analysis of Experiment book, and in fact here 3 responses are included, but we are interested in the yield only for this explanation purpose here. The viscosity and molecular weight, these two also are the 2 response variable which was of interest for the experimenter, but for understanding the second order model point of view, we are not interested to discuss anything about viscosity and molecular weight. So, as a result, what I mean to say that if I write that this part a natural part coded variable for and yield is y, then you see here there are 4 factorial points and 4 axial points and 1 center point. So, as I told you that 9 distinct observations are there. In fact, at the center point there are 5 number of observations which helps us to estimate the error. So, this is what is the data you got, and this is what is the experimental design. Based on this experimental design, this coded variable values are like this, and your y value, response value, the yield value like this. So, with this data we can fit a second order response surface. To fit the second order response surface, we are using the coded values, we are not using the natural variables values. So, but keep in mind that when you conduct the experiment, you set the process with the natural values. When we analyze the experimental data, instead of natural values, we have taken the coded values and then we fit the models. Okay. So, this is what is our model. Our model is y equal to beta 0 plus beta 1 x 1 plus beta 2 x 2 plus beta 1 1 x 1 square, beta 2 2 x 2 square plus beta 1 2 x 1 x 2 plus epsilon. So, this is our second order model involving 2 variables, 2 factors x 1 and x 2. So, this is for first order main effect, this is for second order main effect, this is for interaction. So, this is for intercept. So, 1, 2, 3, 4, 5, 6 parameters to be estimated. So, what is your design matrix? Design matrix is X. So, what you require? You have to write it first x 0, that is your for beta 1, then your x 1 for beta 1, x 2 for beta 2, then x 1 square for beta 1 1, x 2 square for beta 2 2, and x 1 x 2 for beta 1 2. Okay. So, this now how many observations we have? We have used CCD, we have used CCD here, CCD with 4 factorial points, 4 axial points and 1, 2, 3, 4, 5 center points. So, that means 4 plus 4, 8 plus 5, 13. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So, you have 1, 2 like this, the 13 number of observations. So, for x 0 all will be 1, for x 1 that is minus 1, then plus 1, then minus 1, then plus 1. So, like this the last one is your minus 1.414. Similarly, x 2 similar, then you square the x 1 row column, you will get x 1 square, square x 2 square, you will get x 2 square. So, like this you will be and then multiply x 1 and x 2, you will be getting x 1 and x 2 column. So, then what is the resultant column? Resultant column is this. So, first column will be all 1, second column will be minus 4 minus 1 minus 1, okay, minus 1 plus 1 minus 1 plus 1. So, like this what will happen, ultimately you will get this kind of design matrix. So, this is known as design matrix. Okay. So, you just verify, and if there is any mistake you point out in the discussion forum. But this is the procedure. First you find out the design matrix. Once you have the design matrix, then you also have the y values, the 13 y values you have. So, what you require? You require x transpose x to be computed, x transpose x inverse to be computed, x transpose y to be computed, then finally beta cap will be x transpose x inverse x transpose y. That is what we have seen in regression lectures. Okay. Exactly same thing we have done here. First found out the x transpose, then x transpose x, then you see that x transpose x inverse, then x transpose y, and beta is x transpose x inverse x transpose y. This will give you this value. So, intercept is 79.94, x 1 with 9.995, x 2 0.515, then x 1 square minus 1.376, x 2 square in that is minus 1.001, and with x 1 x 2 0.025. What do we mean? I am saying these are the beta estimate. We will write beta 0 plus beta 1 x 1. So, beta 1 is 0.995, beta 2 is 0.1515, beta 1 is minus 0.137, beta 2 is minus 1.007, and beta 1 is 0.025. So, this is your predicted fitting value or fitted regression line. So, if you want the regression equation, then it is y equal to 79.94 plus 0.995 x1 plus 0.515 x2 minus 1.37 x1 square minus 1.001 x2 square plus 0.25 x1 x2 plus error will be there. So, this is your regression response surface. So, if you want fitted value, it will be like this, only error term will not be there, 0.995 x1 plus 0.515 x2 minus 1.37 x1 square minus 1.001 x2 square plus 0.25 x1 and x2. So, this is my response surface, this is what is fitted one, fitted response. This is fitted response surface. Okay. So, now when you fit the second order model, your immediate work is whether the model is adequate or not, and next is whether the parameters estimated are significant or not. So, let us do this. So, using the regression procedure, what you require to do, here you first find out epsilon cap, which is y minus y cap. So, that means you have the 13 observation for y minus 13 observation for y cap, then it will give you the 13 epsilon cap value. Then you find out SSE, SSE will be epsilon cap transpose epsilon cap, means this one. So, it will give you SSE. Then you will get SST from y only. This is nothing but n minus 1 s y square, where s y square is the variance of this, that you know how to compute. So, then SSR, that is basically the regression or model part, you will be getting SST minus SSE. So, in this manner, then R square is basically SSR by SST. So, in this manner, when you compute, you will get this one. You see that R square value is 0.98 and adjusted R square is 0.97, and it is quite significantly high. So, that means model is fit. Now, if you see the ANOVA also the F test talks that is a very high value 79.66. So, that means model is perfectly fit. And now, if we see the the parameter estimated value, that is 79.94, 0.995, 0.515, minus 1.37, minus 1.001, all those things with the standard error, and if you see the t value is quite high except x1, x2, but even then it is also 1.87. Okay, so, these are very high values. So, that means they are significant, and if you see the p value, if you see the p value, you see the p value is very low, and only x1, x2 is significant at 0.1 probability level. So, if 0.05 probability level, we can say the interaction term is not significant. Okay. So, we can say that the second order response surface is a fit one here. Now, question is that, then you may say that why will not go for, why will go for only second order, why not cubic? So, we have gone for quadratic, why not cubic? It may give even better result. Now, quadratic R square is 0.98. So, it is already quite large, very high. So, cubic I think we do not require. But what happened if you use cubic one, then your number of parameters to be estimated will be even more. So, that means you require cubic part x1 cube, x2 cube. So, ultimately what will happen if you go for cubic one, you will find out that there will be some alias structure, means some parameters cannot be estimated completely. So, and with your if I say the probability value is also, you see that cubic 1 0.98, F value is very low. So, that means cubic part is not there. So, as a result, so we can say that second order model is a fit model, and this is what is for today. That I want to say what I mean, what I wanted to tell you, it is clear to me. I hope that you understood that what you will do when you want to fit a second order response surface, what kind of designs you employ for experimentation. Once you get the data, how do you analyze the data using regression and get the parameter estimated. You check the model adequacy, check the parameters of the models, whether they are significant or not. Once it is done, your response surface is ready, second order response surface is ready. Now, this response surface will be used or will be analyzed properly, and to see that the point where we have done the second order experimentation, for example here, whether at this zone is your optimum zone or not, that will be known through analyzing the response surface. So, there are two modes of or two ways we can analyze, using contour plot and using canonical analysis. Next class I will discuss contour plot based analysis and canonical analysis based analysis as well as interpretation. Thank you very much.